drawn in those endpoint ones, sort of, here and here. Might draw over them in a bit. But if you look at it, we've got, so my orange surface on the outside is a cylinder. I've also got an inner sort of spherical surface, and then I've also got conical surfaces. So as a first step, I'd sort of think about the relationship between, Cartesian and spherical and cylindrical coordinates. So we just recall if we've got, so that's sort of the Cartesian coordinates, then if we're just looking in the x, y plane, we might have rho, as in cylindrical coordinates is there. With this angle coming off the x-axis, we call phi, and so we can convert this distance x into rho cos phi, and this distance y rho sine phi. And then in spherical coordinates, we'd have the radius, this radius r, coming down. So that's obviously a right angle too. Got this point here, x. And then the angle theta is coming down from the z-axis. That's a theta there. And so if you're looking sort of in cylindrical coordinates, you've got rho squared equals x squared plus y squared, but then in spherical coordinates, you've got r squared equals x squared plus y squared plus z squared. So we see that is rho squared plus z squared. And I've just sort of put that there because when I'm thinking about the surfaces, it's sort of good to have that reference. So what we want to do is we want to be able to sort of integrate this or set up the integral at the very least to find the volume of this object. And so we need to set up like a triple integral. So for this question, I just sort of thought about the surfaces a bit more. So I started with surface 1. So surface 1 in my case is a cylindrical surface. And it's given by x squared plus y squared equals 9 on 4. So if we go up here, we see that x squared plus y squared is rho squared. So we get that rho is equal to 3 on 2, because that's 3 on 2 squared is 9 on 4. Obviously, it's not negative because rho is positive. Or in spherical coordinates, we get rho, which is equal to r sine theta, is equal to 3 on 2. I don't think I put that one up there. And then I'm going to go on and I'm going to look at this second surface, and so in my case that's this green spherical surface here, and it's given by x squared plus y squared plus z squared equals to 1. So it's just a sphere with radius 1. So that implies that the radius is just equal to 1. And then S3 is the conical surface. And so that's this top conical surface here that goes around like this. And I've said it's given by x squared plus y squared minus 2z squared is equal to 0, where z is positive, because this here is my z equals 0 plane, would be here. So the red part is in the z equals, is a, greater than 0, so z is greater than 0. So we get rho squared minus 2z squared equals 0, or rho squared is just equal to 2z. Oh, we might want to. So you'll note here, so when I take the square root of both sides, oops, there should be a square root there. I take the positive, like I don't have plus or minus here because we see here that z is greater than 0. And then in spherical coordinates, this implies that tan theta is equal to rho on z. So we get, which is equal in our case to root 2, so we get theta is equal to arctan root 2. And then we've got another conical surface that we're going to look at in a similar way. So in Cartesian coordinates, it's being given to us as x squared plus y squared minus 4z squared is equal to 0, where z is less than 0 this time because it's in it's below this z equals 0 point here. So doing sort of the same thing, this x squared plus y squared is rho squared minus 4z squared is equal to 0. So we're going to get rho is equal to minus 2z, because z is less than 0 this time. So, but rho has got to be positive, because that's how it's sort of defined in cylindrical coordinates. So if z is less than 0, then we need this minus 2 here to make sure that rho is positive. So then we get sort of the same thing. We've got rho on z is equal to minus 2 this time, and so if we want to convert that to sort of just that constant angle of theta in spherical coordinates, we get theta is equal to minus arctan 2, because I've taken the minus out the front. So because arctan minus 2 is the same as minus arctan 2. But if I go back to this picture here, this theta is defined from 0 to pi, because we go all the way down to, if the z-axis continues, that's where theta is defined from. So theta equals 0 to theta is equal to pi. So it's got to be positive. So here I'd get a negative angle, but because it's like tan is a periodic function, I'm just going to add pi to fix that, because I've noticed that that's not between theta is equal to 0 and theta is equal to pi. And then S5 is just the plane x is equal to 0. So this, I haven't put it in there, but this is surface 5, this purple one here. And so in spherical coordinates, again, we find that x is equal to 0 is just the constant phi is equal to 3 pi on 2. And then S6 is the plane y is equal to 0, which implies that phi is equal to 0, because the phi comes off the x-axis here. So this is that surface 6 plane here. If anyone has any questions, feel free to stop me anytime. So that's surface 6 there, and so that is this plane y is equal to 0. So if, like this plane here, and you can see that that's got constant phi, this angle here, and we haven't moved off the x-axis, so it's phi is equal to 0. But if we move all the way around to here, and we have the plane here for x is equal to 0, yep, that is rotated through 3/4 of the 2 pi, so it's 3 pi on 2. So, and I've done it like that because we're looking, so in spherical coordinates, if I look at it, the object is sort of created by, if you take one of these these removed panels, so say surface 5 here, this purple one here, and if we just took that, and if as we span it around, it sort of it stayed everywhere I've put it, and we rotated it through the 3 pi on 2, that's how we can create that object. So if we integrate over, as we're swiping that segment through 3 pi on 2 radians, we can find the volume. So hopefully that makes sense to you guys. So if we just think about it sort of in those that surface 5, say, in 2D, so this is sort of the radius here, and we have this inner radius here. Maybe I'll draw that in red. So that's r equals to 1. And then we've got the conical sort of parts that form that boundary. And so they're at constant angles. So this one is at theta is minus arctan 2 plus pi. And then this one is at theta is equal to arctan square root of 2. And then I have messed up this part here because the outside bit is doesn't have constant radius in spherical coordinates. It has constant radius in a cylindrical coordinates. So here it's a straight line because it's a cylinder, and so this is rho is equal on 3 on 2, or in spherical coordinates we get r cos theta is equal to 3 on 2 because this is rho. So we get that r is equal to 3 on 2 that should be sine, not cos, sorry. And so we're going to integrate from r is equal to 1 to r is equal to 3 2 sine theta on 2 sine theta, and then we're going to integrate theta between minus arctan 2 plus pi to theta is equal to arctan the square root of 2, and then we have to integrate phi around that full 3/4 of the circle, so from phi equals 0 to 3 pi on 2. So as theta changes from theta equals minus arctan 2 plus pi to theta arctan root 2, the spherical radius changes from r equal 1 to r equals 3 on 2 sine theta. And this is repeated around the whole, well, 3/4 of the sphere from phi is equal to 0 to phi is equal to 3 pi on 2. So now we can create the triple integral for our volume using all of that. So volume is equal to, so we're going to go phi from 0 to 3 pi on 2. We're going to go theta from minus arctan 2 plus pi to arctan the square root of 2. And then we're going to go r is equal to 1 to 3 on 2 sine theta. And then we've got just in spherical coordinates, you know, that sort of volume dV. And then the question doesn't ask you to evaluate the integral, but you can. You can do that and you can find the volume of the integral. If I have time, I doubt I will. I would go through that. But I think we should move on. So surface 1 in my case was this orange surface, and it's a cylindrical surface there. Does anyone have any other questions about that one? Otherwise, I'm going to move on to question 2. To which part would you like to? That's r squared being integrated. I don't think I've defined a v. Okay, I'm going to move on. So we've got this 2D vector field given by these blue arrows here. My x is sort of going from 1 to 6. My y is -1 to 1. And my vector field is given by xi plus yj. And I'm going to compute these line integrals. So I've got 3 lines from points A, which is at 1, 0, and so this is A here, and this is B at 6, 1, and A is at 1, 0. And I'm going to compute that line integral 3 times, taking different paths each time. So the first one, I'm going to compute the line integral from A to B, where this is just, it's a linear line given by y is x minus 1 on 5. So for all of them, this fxy is equal to xi plus yj, and that's equal to f1 xy I plus f2 xy j. So for my vector field here, my f1 is x and my f2 is just y. And so for question part I, we've got just a linear line. We're going from A to B in this direction. And so my integral from A to B so we want to find f1 dx, f2 dy along the line y is equal to x minus 1 on 5. So we want to find f1 at x minus 1 on 5, plus f2 at x minus 1 on 5. And then here, well, as you can see in the questions, you know, f1 dx plus f2 dy, it's the same as if we put dy dx here, dx. So we need to find dy dx, which in this case, if we find, so it'd just be the constant 1 on 5 dx. So f1 was just x. I don't think I'll have time to do that, but I don't see why not. You'd have, I guess, f1 dx dy dy plus f2 dy from x is equal to, what would that be? 5y plus 1, and then you'd change your limits to y instead of x, because here I'm going to have x is equal to 1, x is equal to 6, and so f1 was x, cool, and then plus 1 on 5, and then f2 was just y in my case, so it's x minus 1 on 5 dx. So I simplified that to this to make it easier to integrate. So I get 13x squared minus x, and we do that from the limits 1 to 6. So we get 13 by 36 minus 13 minus 6 minus 1, which gets me to 18. Did anyone have any questions about that? I'm going to move on to question 2, because I'm worried we're not going to finish. So for this one, this is this green line here. So again, my A is here. I'm going in this direction here. And y is equal to minus cos pi x on 2. So now we get so essentially we're going to do the same thing, except now we've got a different function for y is as a function of x. So I've just written the same thing. Whoops. So f1 at x minus cos pi x on 2 plus f2 at this same value. And then in this case, my dy dx is going to be We get rid of the minus, because if you integrate cos, it's minus sign. We get pi on 2 coming from this constant in here, sine pi on x on 2 dx. So again, we're going from x equals 1 to 6 still, and f1 is still just x plus I'm going to put a minus there because it's f2 is y, so it's minus pi on 2 cos pi x on 2 sine pi x on 2 dx. And we can use the double angle formula there to get minus pi on 4 sine pi x dx. And so now it's pretty easy to integrate. We get x squared on 2 plus 1 on 4 cos pi x from 1 to 6. So we get 36 on 2 plus 1 on 4 cos 6 pi minus half minus 1/4 cos pi. So we get 18 plus 1/4, because cos 6 pi is 1, minus 1/2, plus another 1/4, because cos pi is -1, so we still get that equal to 18. Which, if you've looked ahead to part 4, and you notice that it's suggesting that it's a conservative vector field, the fact that they're the same makes sense. So I'll move on to part 3 now. So now it's the same thing, except we've got it's parameterized now. It's a parameterized line. So this purple line is given by r of t, so where that's 5 sine t plus 1, I plus 2 on cos t plus 1 minus 1 j. So this one, a is at 1, 0 still, which is where t is equal to 0, and this point here is b 6, 1, and t is equal to pi on 2. We're still going in this direction from A to B. And if r is equal to, as it's given there, then we can find dr dt, because we'll need it, when we're finding the line integral. So I'll just find it out here first. So I think I changed my question without, because that's not that line, that purple line. I'm just going to draw it. Ignore this. RT is going to be given by 6 on 5 cos t plus 1 I plus 1 minus cos t j. T is still going from 0 to pi on 2. Sorry about that. I think this is the question I actually did, so let's go with that. So dr dt, I'm going to get, so I'm going to get 5 cos t plus 1 squared on the bottom, and then I'm going to get a 6 by 5, so a 30 sine t on top, I, plus a minus minus, so a sine t j. And then my f of xt yt is going to be equal to xt I plus yt j. So that's 6 on 5 cos t plus 1 I plus 1 minus cos t j. And in this case, it's just the same as RT, because my vector field is just xi plus yj. And so now we want to find this part here, this f of r of t dot dr dt. So my f of r of t was yes. This, because, yeah, cool. So f of r of t, it's going to be 6 over 5 cos t plus 1 I plus 1 minus cos t j dotted with dr dt. So that was 30 sine t 5 cos t plus 1 I plus sine t j. So that's going to be equal to, so 6 by 30, I'm going to get 180 sine t over 5 cos, I think I've left out, that should be squared down the bottom here. And then I'll get cubed here, plus, and then sine t by 1 minus cos t. So we get sine t by 1 minus cos t. Or I might decide to expand that out. And so now our integral that we're looking for so we just want to integrate what we found here, this f dot dr dt. And we're going to do that from t is equal to 0 to t is equal to pi on 2. And then, so I actually split that up into to 3 parts of the integral. So for first term in integral, I let 5 cos t plus 1 equal to u. Then I get du is equal to minus 5 sine t dt. And t is equal to 0 implies that u is equal to 6. T is equal on pi on 2 implies that u is equal to 1. And so the integral is equal to from 6 to 1 u minus 36 on u cubed du plus, and so these other ones I just kept, I just integrated with respect to t because that was easy to do. So I get minus cos t from 0 to pi on 2 for the sine t part, and then I get minus cos squared on 2 from 0 to pi on 2. And now this one's much easier to integrate. I get 18 on u squared from 6 to 1 minus cos pi on 2 minus cos 0 plus cos squared pi on 2 over 2 minus cos squared 0 on 2. So I get 18 on 1, so just 18, minus 18 on 36, minus 0 minus 1 plus 0 minus a half. So I get 18 minus a half plus 1 minus a other half. So these parts all cancel and I still just get 18. So it's still just the same answer. And then for part 4, if I look at df2 dx minus df1 dy, I just get d dx. So in my case, f2 was y minus d dy, and in my case, f1 was x. So dy dx, y does not, it's a constant as far as x is concerned, so we get 0, and the same goes for x if we're differentiating with respect to y. So 0 minus 0 is 0, which means that f is a conservative vector field. Because if this is equal to 0, it's a conservative vector field. And so now, if we let f equal to grad g, where g is a function of x and y, we get that f1 I plus f2 j is equal to dg dx I plus dg dy j, which if we break that down into 2 equations, the I parts have to be equal. So f1 is equal to dg dx and f2 is equal to dg dy. And so this is equal to x because f1 is equal to x and f2 is equal to y. So they're my two equations. Now, integrating 1 with respect to x gives, so dg dx is equal to, so dg dx we said was equal to x because it's just equal to f1. So we're integrating with respect to x dx. So that implies that our function g of x and y is equal to x squared on 2 plus some function of y. Does that make sense to everyone? Because this has sort of disappeared when we've differentiated and gone back the other way. So we can't see anything about y when we integrate that part. But g must also satisfy 2 as well. So from that we get d, so the partial dg dy x squared on 2 plus hy is equal to y, because we had dg dy is equal to y. So this x squared on 2 part, if we differentiate with respect to y, it just disappears. So we just get, and so now again, if we integrate this with respect to y, with respect to y, that gives dh dy dy is equal to y dy. So that implies that h of y is equal to y squared on 2 plus k. So this time, so h is only a function of y. In the first case, when we were integrating, like g was a function of x and y, which is why we had plus a function of y, which could include a constant, you know. But now h is just a function of y. So when we've integrated, it's y squared on 2 plus k, which is a constant that we don't know about. So we found that g of x, y is equal to x squared plus y squared all on 2 plus this constant k. K is a real number. We don't know what it is. We don't have enough information to find it. But from that, if we find, if we look at the function g at D and the function g at point A, we get g at 6, 1 minus g at 1, 0. That's 6 squared plus 1 squared on 2 plus k minus 1 squared plus 0 squared all on 2 minus k. So the k's cancel now. We get 37 on 2 minus 1 on 2. So we get 36 on 2, which is equal to 18, which is the same answer as we got for parts 1 to 3. So this confirms our answer. So because it's a conservative vector field, it doesn't matter which path we took from A to B. When we do the line integral, we always got the same answer. So perhaps you would take the most simple line from point A to B, and use that to find the line integral if it's a conservative vector field, rather than, doing 3 loops, on your way there. Now, I think I've run out of time for question 3. I did have one set up, but it's pretty similar to question 2, except now we're doing closed paths rather than sort of just from point A to point B. We're always coming back to this point here, point 2 minus 1 in my question. And you'll also note that part 4, we're showing that F is not a conservative vector field. So mine was F was yi minus xj, and so df2 dx minus df1 dy, I get d dx of minus x minus d dy of y. So I get minus 1 minus 1 is equal to minus 2, which is not equal to 0. So it's not a conservative vector field. So you're not, the path that you take does matter. And if you go sort of there and back again from a point, as if you were doing a closed loop, you're not going to get 0. So your answers should, I wouldn't be like, don't be worried if you get different answers for these ones. Does anyone have, I could probably go over part I, like question 3, 1, 2, or 3 quickly. Does anyone have a preference on which one I look at?
Number 2, probably.
Part 2. Okay, I'll see how I go with this one. So for this one, I'm going from the point 2 minus 1 here, and I'm going along this slightly curved line to the point 5 minus 2 that way, and then, oops, should be a linear line. I'm not very good at drawing straight lines on this. And then C2 is going to be this straight line here. So C1 is given by minus the square root of x minus 1, and C2 is going to be given by just the linear line minus x minus 1 all on 3. So if I look at this closed integral here, that's going to be the sum over I, the 2 lines of each curve here. So the first one, I'm going from the point 2 minus 1 to 5 minus 2. And then it's sort of the same as before. If I break it down like this, f1 dx plus f2 dy on y is equal to minus x minus 1. And sort of going back to your question from before, Oliver, I think, asked this question. So when you're doing this rectangular one here, it's going to make sense to do, particular curves with respect to x and particular curves with respect to y. Otherwise, you won't be able to do that. But, in this one, y has been given as a function of x, so I'm just going to do it like that. And then you'll do the other one. It goes back the other way, so from 5 minus 2 to minus 1. and it's the same thing. Oh, sorry. It's almost the same thing, except that the line is different. I've drawn the same line there. So that was minus 1/3 x plus 1. So the first one would be like this. And then we'd need this dy dx here. We're going to do it like that. In this case, that's minus 1, 2 over the square root of x minus 1. And so if we're just integrating with respect to x, I just need the x limits really. And that's going to be f1 x, and this time, you know, y is going to be minus 1/3 x plus 1 plus f2 x minus 1/3 x plus 1. And then that same sort of, you know, dy dx and the dx goes there. So in this case, dy dx is just constant minus 1 on 3. And again, we just need the x limits really because we're integrating with respect to x. So 5 to 2. So my f1 for this vector field was just y. So that was minus the square root of x minus 1 dx plus f2, which in this case was minus x. So and then that was by dy dx. So I get minus x is x, but by this is minus 1, so plus x on 2 root x minus 1. I think I got confused because I already put the dx there. That looks like a du, but it should be a dx. And then the second integral here is from 5 to 2. So again, f1 is y minus 1 on 3 x plus 1. So my f was y I minus xj. So I'll just put that there. And then, so then it's f2 is minus x by dy dx, which is minus 1/3, is just plus x on 3 dx. Now, I'm not going to go into integrating these because we've run out of time, but if you want to complete it yourself and check your answer, you're going to get minus 1 on 3. They're not the best functions to integrate though. I think yours are a little bit easier, so I wouldn't be too worried about that. But essentially, it's pretty much the same as question 2, except now we've got a closed path rather than just a line integral, if that makes sense. Does anyone have any questions about either question 3 or the other questions that we went over before I go? I'd also suggest that I don't know if I don't think the solutions are released yet, but for your most recent assignment and also assignment 6 that were both in class, I think because if you've attempted all questions, you get full marks. It is a good idea to sort of check what you might have done wrong when the solutions come out, to look over it and don't just assume that you got 20 and therefore you did everything correctly. But yeah, I'll talk to you guys again next week.
Catherine?
Yes.
Okay, I probably have this all in my notes and that, but while we're here, when you've got the f1 dx, right, in the integral, and you're holding y equals negative square root of x minus 1.
Yep.
This is probably very obvious, but how did you get let me go check my notes again. I'm sorry, I'm missing a step somewhere.
Is this for this question 3?
Yeah, see where you are there?
Yes.
How do you get from there to 2 equal signs down?
So here, what have I? So my f1 was y.
Yep.
So in that case, it's minus x minus the square root of x minus 1. So that's what I've got here.
Okay.
And then my f2 is x.
Sorry,
minus x. So I get minus x.
Yeah.
But that's being turned into plus x because I also multiply it by dy dx, which I found to be minus 1 over 2. So this term here is minus x by minus 1 over 2, the square root of x minus 1. Does that make sense?
Yeah. I think what confused me is that we're holding the y constant in that first one, and in the second one, we're holding it constant again, but it's a different thing. So when we do the f1s and f2s, if x or y is held constant, we substitute that into the f1 or f2.
Yeah,
as we do it.
For that particular integral, because the paths here.
2 different ones.
Yeah, they're 2 different. So you've got this path is given by a different function to this path.
Yeah, that's great.
Yeah.
Okay, that's made it a lot clearer. Thank you.
Because it's not a conservative vector field, it does matter what path you're taking. So you can't go, oh, that path seems a bit awful. I'll just do something else. You can't do that because it's not a conservative vector field.
Okay, that's brilliant. Hey, thank you very much for that.
No problem.
Greatly appreciated. Thank you. And thank you for the feedback too on the last assignment. No problem. Greatly appreciated. Thank you.
Talk to you next week. See
ya.
Catherine, I've just got a question as well.
Yeah.
I think it was your second last line to the last one. I think it's where you changed.
The same question?
Yes. I think, where you changed f of 1, x, and what y was the same too. And then how did you get to the last one after that?
You don't mean this?
No,
one?
Sorry.
No, sorry. Here?
Yeah, so from that one, line before to that one.
So F1 is y.
Yes.
So that's this minus for this integral, this first part, it's at y equals minus the square root of x minus 1. So that's that y there, and then it's minus. So if I did it like, it would be y minus x dy dx. And so this is dy dx, and then this is the x, and then this is what y is equal to at that point. And then I've done the same again. I've done y minus x dy dx. But this time the y is given by this, and the dy dx is this time is equal to, so if y is equal to minus 1 on 3 x plus 1, then dy dx is equal to minus 1 on 3. So minus 1 on 3 by minus x is x on 3.
Yeah, got it. I think
And
it's
then
just
this,
yeah.
this one, you know, y is equal to minus the square root of x minus 1. The dy dx is given by that minus 1 on 2 x minus 1. Does that, so like they're the same on both integrals, but the limits are different, and the path that we're taking is different. So y as a function of x is different.
Yeah, got it. I think it's just because you skipped a couple of steps there and it lost me a
Yeah.
little bit. It's all good.
I was running out of time, so I
Yeah,
tried
no,
to
fair enough.
cover as much as I could, but
Yeah.
sorry.
No, that's all good. That makes sense now. Thank you very much.
Great. Does anyone else have any questions? No? I'll see you guys next week.